Combustion analysis. The idea here is that if you burn something, you can calculate what it is that you burned. After all, a certain amount of the products, carbon dioxide and water, belong to the carbon and hydrogen and other elements that you started with. Let's go ahead and do an example. The key here is that every time you burn something containing carbon, it'll make 1 mole of carbon dioxide. And it'll also make some water, but for every 2 hydrogens that are formed, that comes from 1 water molecule. So, well, here's a problem. You got 2.4 grams of something. It's toluene, but let's assume we don't know what the formula is. And we're burning it. And we find that we get 8 grams of CO2 and 1.877 grams of water. That's a lot more than the 2.4 grams that we started with, but after all, it forms a lot of oxygen in the product. So what's the simplest formula for toluene? That's code for empirical formula. And we start with what we're given. So that 8 grams of carbon, since 44 grams of 8 grams of carbon dioxide, since 44 grams is a mole, and each mole corresponds to 1 mole of carbon, we must have 0.01823 moles of carbon that we burned. You could write C 0.1823 as a subscript, and that's what I normally do. I just put it right there. Similarly, we formed 1.877 grams of water, but 18 grams of water is a mole, and we have 1 mole of water contains 2 moles of hydrogen. So that back calculates how much hydrogen you must have started with. And it's 0.2083 moles of hydrogen. Normally these give a nice sweet ratio of 2 to 1, or maybe say, 1.5 to 3, something like that. In this particular case, you end up with a different ratio. Note that we've accounted for all 2.4 grams in the starting material, so there's nothing else in it. Toluene is a hydrocarbon, so we are ready to figure out what the heck we got. You take that mole ratio, in a way you're done, right? This is your formula, but it just doesn't look good. We want whole numbers. Try to remember this little mnemonic, divide by the little guy. The smaller one is the 0.183. So if you divide both sides by that, it'll by definition make that a 1, and this some other ratio. In this particular case, and this is very rare, we get a strange ratio, 1 to 1.143. Now, 0.143 is exactly a 7th, and this very rarely happens. So you have to multiply this out by 7 in order to get a whole number ratio. This is a good example of why it's important for these calculations to use a lot of precision, at least 2 decimal places, preferably 3 or 4. And so we multiply everything by 7 and we get C7H8, and that corresponds to toluene. Let's do another example. This can have another element. Isopentyl acetate, which I'm sure smells good. Oh yeah, it smells like bananas. Has carbon hydrogen, and this time they're telling you it also has some oxygen in it. So combustion analysis of 1 3/4 grams of this stuff gives some water and some carbon dioxide. Let's find the simplest formula, hint empirical formula, for isopentyl acetate. Let's start with what we're given, the carbon and the hydrogens, back calculate how many moles we must have started with, and in this particular case you're going to end up with a little bit short. The rest must be oxygen. So let's run it through. We got 4.142 grams of carbon dioxide. Just like before, 44 grams is a mole. Notice top left to bottom right, the units always cancel, so I'll bet it's going to say a mole of carbon dioxide down there, and it does. Corresponds to 1 mole of carbon. That's true, right? These are always equivalent. There is 1 mole of carbon in a mole of carbon dioxide. So we must have started from 0.0941 moles of carbon. For water, it's a little different since 1 mole of water contains 2 moles of hydrogen, but it still weighs 18 grams per mole. Notice this is identical to our previous example, so when you drill these, they get a lot easier. And every mole of water contains 2 moles of hydrogen. We started with looks like twice as many moles of hydrogen. This looks like a 1 to 2 ratio if I had to guess. But have we accounted for everything? The way I do it is I figure out how many grams that is, and when you do, it's only 1.3189 grams of this. Now, you do need to point out that, let's see, 1.3189 grams. Yeah, you'll note that we're a little bit short, and you would have to calculate that. So 0.4311 grams must be oxygen. So let's figure out how many moles that is. So we get a total mole ratio. Don't run into the mistake of calling this 32 grams of O2. That's true, oxygen tends to form O2, but only when it's by itself. This is just O, so 16 grams is a mole, so our ratio there is 0.02694. What's our rule for getting whole numbers? Divide by the little guy. So when we take that and divide by the smallest one, which looks like the 0.02694, note the high level of precision in order to get good data, we end up with C3.5H7O1. That's not uncommon. It should be obvious at this point we need to double everything for a final answer of C7H14O2. And that's one possible isomer, and that is isopentyl acetate. So it matches what we wanted it to match. In other types of problems, they will then tell you the actual molecular weight, and it's usually some multiple of this stuff, and then so you have to scale appropriately. But this is typical combustion analysis problems leading to an empirical formula.